Methods for solving quantifier linear equations for formation of optimal queries to databases. The work is devoted to the study of the algebra of linear predicate operations, the properties and methods of assignment, as well as methods of the application and the description of various regularities, methods of solving quantifier linear equations. The developed algorithm can be used in the production of linguistic support for automated information systems, in information search systems, in solving problems of logical inference in databases and expert systems, as well as in solving problems of recognition and classification of objects. The method of solving logic equations implemented in the software system will greatly reduce the number of necessary calculations. The purpose of this work is the algorithmic implementation of the method of solving quantifier linear equations based on the algebra of linear predicate operations, the formal operators of linear logical operators, and methods of solving logical equations. The main tasks of the research are analysis of formal methods of intelligent systems, analysis of logical algebraization methods, study of the operators of logical spaces, the algebra of linear predicate operations, study of the theory of linear logical operators. The rapid development of technologies determines the high rate of development of methods for creating intelligent systems for various purposes. Currently available intelligent information systems are able to perform functions that were previously considered the exclusive prerogative of humans: prove mathematical theorems, translate text from one language to another, diagnose diseases, and perform many other functions. However, in the future, an ideal computing machine should surpass human abilities to think logically, analyze the information received, solve the most complex problems, and interact with the environment. Relational and logical methods of knowledge representation play an important role in the development of mathematical support for information systems. One of the effective universal mathematical methods for describing information is the algebra of predicates and predicate operations. This language of algebra is easy and convenient to describe various formalized information, form queries in databases, and model human activity. In various computerized industries, there is a need to process information displayed in natural language. In an automated computer system, which includes a person as its organic link, the main form of information transfer is served by documents containing a significant amount of textual information. Computer modeling of text processing will allow automating many types of human intellectual activity, expanding its capabilities. The basis of automated computer system is automated information systems, the purpose of which is to automate the process of information accumulation, search, and generalization. The effectiveness of automated information systems is recognized by their ability to process unformalized or weakly formalized information. A characteristic feature of the operation of modern intelligent systems is that the data processing is based on the necessary knowledge of the problem industry entered in advance in the knowledge base of the system, while previously created systems worked with data that were simply processed by various programs. A rather vast number of works have been devoted to the study of the difference between data and knowledge, the main idea of which can be formulated as follows. Knowledge is a complexly organized type of data that differs from traditional ideas about data in four main features. Knowledge placed in the record contains not only the information part, but also the descriptive part. It stores all the data about the information unit that may be needed in the user's work with the system. Knowledge is in the knowledge base creates complex hierarchical structures, which is achieved by introducing various relations between information units entered in the knowledge base. Informational units reflecting knowledge can be composed into more complex organized units and decomposed into simpler ones. Attached or built-in procedures can act as part of information units characterizing some knowledge, which allows these procedures to be activated as a result of appearance of various information units or connections between them in the knowledge base. Depending on which difference two base databases or knowledge bases discussed earlier, it is necessary to proceed from advantageous query and response algebras. In each case, the database in the main approximation can be considered as an automaton of type L, U query and U result. Representation of the database in the form of an algebraic structure is shown to be useful in various cases. For example, in cases where it is necessary to determine the deviation of compositions and decompositions of databases, as well as from isomorphism and equivalence. The algorithm can be described as follows. On the input comes the data about the modeled system, the dimension of the problem, semantic features, a system of logical equations, and a set of resulting variables. After processing this data by the software system, during which the consistency of the system of logical equations is determined and the non-essential features are turned off. At the output, we get the entire array of solutions of the system of logical equations. The example given illustrates the possibility of using the theory of linear logical operators and the method of solving the quantifier predicate equation for processing and storing information in databases. Suppose that the database contains information about 4 factories that produce parts for cars. Assume that we have 4 factories from F1 to F4 producing parts from D1 to D4 like shown on the slide. The existing factory part relationship is easily described by the following binary predicate P1. The next problem is to obtain information about which plant produced part D1. The corresponding predicate revealing this requirement is written in the second form P2. As a result, the predicate P3 corresponding to the sought information is denoted by a quantifier equation of this. There exists diff of for P1 and P2 equals P3. Form and set the following relation P3. The solution of this quantifier predicate equation is obtained from the solution of the corresponding operator equation A times X equals Y. The matrix of operator A has the following form and vector X as shown. As a result of the action of the operator A on the vector X, we get the vector Y, and meaning that the part D1 is served by factors F1 and F3. Thus, the operation of searching for information of interest in the database is replaced by the operation of operator multiplication. Next, let's assume that the database contains information about which parts are used in certain cars, as shown on the slide. The relationship car part corresponds to the binary predicate K1. Similarly, as a previously considered case, it is easy to extract information about which cars and which parts are used from the database by solving the corresponding quantifier predicate equation, replacing it with an operator equation. Suppose that now it is necessary to solve a more complex problem, to calculate which factories produce parts for a specific car. The following system of quantifier predicate equations corresponds to this condition. We can display this system in the form of single equation. The quantifier predicate equation corresponds to an operator equation of the form b times t equals x. The logical vectors t and x are constructed respectively from the binary predicate k2 and k3. The linear logical operator t has a matrix form built on the binary predicate k1. Therefore, the predicate equation corresponds to the operator equation of the form A times B times T equals X. We can transform it to F times T equals X, where the linear logical operator F is equal to the superposition of operators A and B. In this case, we have such results. In this way, a rather large search in the database is reduced to the calculation of the matrix of the operator F using the operation of multiplying the matrices of the operators A and B. For example, if we calculate which factories manufacture parts for car C1, the corresponding logical vector T has the form 1, 0, 0, 0. As a result, we get that the manufacturers of parts for the car C1 are factories F1 and F2.